Okay, let's dive into some really interesting source material today. We're looking at electric potential and voltage.
Yeah, these are super fundamental concepts for understanding how electricity really works, you know?
Absolutely. From tiny circuits right up to, well, global power grids.
Mm.
We've got some good notes and articles here.
hmm They really help unpack these ideas. They give us the definitions, the crucial links to electric fields.
And ways to visualize things, which is always helpful with invisible forces.
Exactly. And show why potential is such a key tool in physics and engineering, too.
So our goal here is to really get a handle on what electric potential is, how it connects to the electric field we've talked about before.
See how we can picture it, maybe with analogies like potential hills or these equipotential surfaces they mention.
Right. And just understand why looking at things this way is so, well, powerful. It's like getting a new perspective on the electrical energy landscape.
It really is about the energy side of electrostatics. You
Hmm.
know, how energy is stored, what drives charges to move, and what that looks like in space.
Okay, so let's jump right in. What's the absolute core idea? Electric potential, symbol V.
Well, the simplest definition is it's electric potential energy per unit charge.
Per unit charge, okay.
So if you imagine placing a tiny test charge, let's call it Q euro, at some point, and it has potential energy U there,
Uh-huh.
then the potential V at that exact point is just U divided by Q rho. V equals U over Q rho.
Got it. So it's like asking, how much potential energy would 1 coulomb of charge have right at that spot?
Exactly. It's a property of the location influenced by all the other charges around, not just the test charge itself.
Which is a key difference from potential energy, which depends on the charge you place there.
Right. And another big thing, unlike the electric field, E, which is a vector, it has direction.
Potential is scalar?
Just a number, no direction. And, you know, that often makes calculations a bit easier.
And the unit, that's named after someone important.
Yes, the volt, capital V,
Yeah.
named after Alessandro Volta. And it comes straight from that definition. 1 volt is 1 joule of energy per 1 coulomb of charge.
1 JC. That makes perfect sense. Energy per charge.
And like the electric field, this potential exists as at a point in space, even if you don't physically put a charge there.
Right, it's part of the field created by the source charges.
Precisely. It sets up this, well, energy landscape. And sometimes, you know, figuring out this scalar potential landscape first is actually a much easier way to then find the vector electric field, especially if the charge setup is complicated.
Ah, strategic advantage.
Okay.
So potential is energy per charge, scalar, measured in volts, JC. How does this relate back to the electric field vector, E? There's a key rule, right?
There is, and it's fundamental, basically. If you move in the same direction as the electric field lines, you're moving towards regions of lower electric potential.
Lower potential, okay.
And if you move against the direction of the electric field, you're moving towards regions of higher potential.
So E always points downhill in terms of potential.
Exactly. Downhill is a great way to put it. E points in the direction of decreasing V.
That seems pretty intuitive for, say, a single positive charge.
Yeah.
The E field points out away from it.
Right. And as you move out, away from the positive charge with the field, the potential V gets smaller, it decreases.
Yeah.
If you move inward towards the charge against the field, V increases. Potential is highest near the positive charge. It's like a potential hill.
Okay, hill for positive, but what about a negative charge? E points inward towards it.
Good point. So if you move outward from a negative charge, you're moving against the inward field. So potential V increases.
Increases. But wait, potential near a negative charge is negative.
Right. So increasing here means becoming less negative. Maybe going from -10 volts closer in to -5 volts further out, moving towards 0 far away.
Ah, I see. So it's still increasing algebraically, becoming less negative.
Exactly. And if you move inward towards the negative charge with the field, potential decreases, becoming more negative. The rule holds. E always points toward lower V.
Got it. And this downhill idea, it directly tells us how charges naturally move, doesn't it?
It does. Think about a positive test charge. It feels a force in the direction of E.
So it wants to go downhill.
Precisely.
Okay.
It's pushed from higher potential regions to lower potential regions. It spontaneously falls down the potential hill, seeking lower potential energy.
Just like a ball rolling downhill under gravity.
It's a very similar principle, but now a negative test charge, it feels a force opposite to E.
So it wants to go uphill.
Right. It naturally moves from lower potential regions to higher potential regions. It gets pushed up the potential hill made by a positive charge, or you could say it falls into the potential well of a negative charge.
Well, okay, so negative charges seek higher potential.
Yes, which for them corresponds to lower potential energy. It can be a bit confusing with the signs, but the core idea is they move to minimize their potential energy.
The material also gives the math connecting potential difference and the field. VAM minus VB equals minus the integral of E dot dl from B to A.
Yeah, that integral form is really the mathematical statement of the relationship. It tells you the potential difference VAB, that's potential at A relative to B, is the work done per unit charge by some external force if you were to push a charge slowly from point B to point A against the electric field.
Work per charge to move it against the field.
Okay, and the units work out nicely too, right? Electric
Yeah.
field is newtons per coulomb, NC. And the integral involves multiplying by distance, meters, m. So NC times m, that's newton meters per coulomb.
And a newton meter is a joule.
Right, so joules per coulomb, which is volts.
Exactly. It all connects. So you can actually express the unit for electric field E as volts per meter.
That really shows it's about how potential changes with distance, like a gradient.
Precisely. The stronger the field, the steeper the potential gradient, the faster V changes per meter.
That VM unit makes the link very clear. Okay, speaking of visualizing, you mentioned potential hills and wells. Yeah, they're useful mental pictures. A positive charge makes a potential hill around itself. High potential, close by, dropping off as you go further away.
So a positive test charge placed near the top would just whoosh, accelerate away, rolling down that hill.
Exactly. And a negative charge creates a potential well. The potential is lowest, most negative, right near the charge.
So a positive charge would be pulled into that well.
Right. And this leads nicely into another visualization tool the sources talk about, equipotential surfaces.
Like contour lines on a map.
That's the perfect analogy. Contour lines connect points of equal altitude. Equipotential surfaces are, well, surfaces in 3D space where every point has the exact same electric potential, V.
So if I move a charge anywhere along one of these surfaces,
Its electric potential doesn't change?
which means its potential energy doesn't change.
Correct. And that implies the electric field does zero work on the charge if it moves along an equipotential. Work is only done when you move between different equipotentials.
Okay. And just like map contours tell you about the terrain.
Equipotentials tell you a lot about the electric field. There are some key properties.
Right, the material highlights a few. First one, electric field lines always cross equipotential surfaces at right angles, perpendicular.
Always. Think about it. The E field points in the direction of the steepest decrease in potential. An equipotential surface is a surface of no change in potential. The direction of steepest change has to be perpendicular to any direction of no change. Like walking straight down a hill is perpendicular to walking sideways along a level contour line.
Makes sense. Second property, where equipotentials are packed closely together.
The electric field is stronger. Just like closely packed contour lines means steep terrain, the potential is changing rapidly over a short distance.
This is where they're spread far apart.
The E field is weaker, the potential is changing more gradually, flatter potential landscape.
And the last one we already established, E always points from higher potential surfaces towards lower potential surfaces, downhill.
Always downhill. So looking at diagrams of equipotentials is really informative.
Let's look at some examples for just a single positive point charge.
The equipotentials are perfect spheres centered on the charge. Higher potential values closer in, lower values further out. And the spheres get more spread out as you go further away because the field weakens.
And the E field lines point radially outward, perpendicular to those spheres. Checks out. What about a uniform field, like between charged plates?
There, the equipotentials are flat planes, parallel to the plates and perpendicular to the uniform E field lines. If the field is uniform, the planes are evenly spaced. Potential decreases linearly as you move along the field lines.
Okay. More complex cases, like two equal positive charges.
The equipotentials get pushed away from the region directly between the charges. They sort of bulge out. The potential is high near each charge, but there's a kind of saddle point or flatter region between them where the fields partly cancel.
So the equipotentials would be more spread out in that middle region, showing the weaker field.
Exactly. And for a dipole, equal positive and negative charges.
What does that look like?
Very different. The field is strong between the charges, so the equipotentials get bunched up tightly in that region, showing a rapid change from high potential near the positive charge to low negative potential near the negative charge.
And there's probably an equipotential surface right in the middle where V is 0.
Yes, typically a plane midway between them, if they're equal and opposite, it's a really distinct pattern.
Okay, so these visualizations are powerful. Now, how does potential relate to, say, conductors and actual electric current?
Right, connecting back to practical things. So in electrostatics, when charges aren't moving overall, we know the E field inside a conductor is 0.
The free charges rearrange themselves to cancel any internal field.
Exactly. They might be moving randomly at high speeds, the free electron zipping about, but there's no net flow, no current.
But what happens if we do establish a field inside, say, by connecting the conductor ends to a battery, that creates a potential difference?
Now things change. That potential difference creates an electric field E inside the conductor. And this field exerts a force, FQE, on the free charges, like electrons.
But they're not in a vacuum. They can't just accelerate indefinitely.
That's the key. They're constantly colliding with the atoms of the conductor material, billions of times per second. It's like trying to run through a very dense crowd.
So the field gives them a little push, they accelerate briefly, then bam, collision, lose energy, get pushed again.
Exactly. The net effect isn't continuous acceleration, but a very, very slow average motion, superimposed on top of their fast random movement. It's called the drift velocity.
And that's the electric current, this incredibly slow group shuffle.
That's it. The drift velocity might be millimeters per second or even slower, while the random speeds are huge. But it's that collective drift, driven by the E field, which exists because of the potential difference, that constitutes the current we measure.
Wow. It's amazing that such a slow drift creates the effects we see.
It is, and when we analyze circuits, we often need a reference point for potential.
The 0-volt point.
Yeah. Conventionally, we often define the negative terminal of a battery or a connection to the earth, ground, as having 0 potential, V0.
But that's just a choice of baseline,
Yeah.
correct? Doesn't mean there's no energy there.
Absolutely. It's just a reference. The positive terminal is then at, say, plus 1.5 volts or plus 12 volts relative to that 0 point. The crucial thing is the potential difference that drives the current.
Got it. Useful convention. Lastly, the source material points out a little notation trap.
Ah, yes, the V versus V. Easy to mix up.
Italic V for the quantity, potential, or voltage.
And non-italic V for the unit, the volt. You have to watch the context and the typography if you're reading carefully.
And also maybe be careful with using delta V.
Yeah, sometimes V for potential difference can be ambiguous. Does it mean V final minus V initial or the magnitude? Using VAB, meaning Va minus V, is often clearer about which potential is higher. Just requires a bit of care.
Good tips. Okay, so stepping back from this deep dives, the big picture seems to be that electric potential gives us this really useful scalar way to think about the energy involved with electric fields.
Yeah, it's an alternative perspective to just looking at the force vectors of the E field. Often simpler, and it directly relates to energy, which is so important.
And those equipotential surfaces, they're not just abstract math. They really help visualize the field, where it's strong, where it's weak, which way it's pointing.
Definitely powerful tools for understanding. They map out that energy landscape we talked about.
So these ideas, potential difference, equipotentials, they're really at the heart of understanding why charges move, how electrical energy is stored and transferred, and ultimately how electric circuits function.
They are absolutely fundamental.
And maybe here's a final thought for you to chew on, based on what we discussed. Think about that drift velocity again. You have trillions upon trillions of electrons in a wire, all moving randomly at incredible speeds, bouncing around chaotically.
Utter chaos at the micro level.
But apply a potential difference, create that electric field, a gentle slope on the potential landscape, and suddenly, amidst all that chaos, there's this tiny, almost imperceptible collective nudge, a slow, coordinated drift. And that is the electric current powering our world. It's quite something to realize how macroscopic order emerges from that underlying microscopic randomness, all thanks to potential difference.